Hi, good evening, and welcome to the ZP Developer Zone webinar. So we like to do this webinar once a week, and it's really just answering technical questions that have come in during the week. So first of all, I just want to kind of go through, today's the 23rd of November, just to say that there'll be some links underneath this webinar, and some of those links will actually link to products, and if you buy the products off our web store, you can use this discount code, which I'll also put underneath the in the description once we've gone live, and you can essentially use that to get 10% off in November 2024. With that said, there's also a link to the web store there as well, so that'll help. So any links you see or any discount codes, I'll make sure I put them underneath the video once we've finished going live here. So this is a live streaming webinar, and we're answering questions that have come in during the week. So I suppose I shouldn't really spend so long. I've talked about electrode wheel. This is just a way of arranging electrodes in a kind of circular fashion. There was something like this actually several years ago. Somebody did a glucose strip like this. I really can't remember if it was, it would have been a Johnson & Johnson, which was Life Care, or an Abbott or a Roche. I suspect it was an Abbott or a Roche, but anyway, I'll talk about that anyway. I'll also talk about measuring caffeine. This is an important one to me because often on this channel I say, one of the biggest problems in the world of academic translation or just startup is reproducibility of screen printed electrodes. And that's the show that we are actually getting good reproducibility. I do have a contact, I think it's in Hungary, who often reaches out to me when they've got a few questions around EIS, impedance spectroscopy. So they sent me something fun about the impedance spectroscopy of fruit. I'll only mention that very briefly. We have launched the analysis of lead. In fact, I know I mention it every week, but I'll do the same today. I'll mention the Sensi All platform. I'll mention our screen printed electrodes quite a bit. This is a very new type of potentiostat. That's both a potentiostat and what we call a minimally viable product. So that will pop up today. And the relevance of that will come up when we talk about lead. Somebody's asking about our pH, glucose and lactate sensor, so I'll discuss that. Just a paper also that's come up, laser-induced graphene. I think laser-induced graphene, I can see the kind of, I can see the benefits in terms of giving you extra maybe sensitivity because it'll roughen up the surface area. I'm not entirely convinced that graphene is this like amazing material. Now I'll also discuss MIPs today as well, molecular imprinted polymers. I'm not entirely convinced that MIPs is a great technology. I will talk about aptamers today, and I will talk about antibodies, and I'll talk maybe not so much about enzymes, but aptamers, antibodies, enzymes, receptors, ionophores. These do seem like good groups of molecules for doing detection. I just got a little bit of a problem with MIPS. So now it's a personal comment, and other people are much more convinced than I, but that MIPS will also be mentioned today. In fact, MIPS, Lysozyme, the nice thing about MIPS, I would say, is molecular imprinted polymers. It's at least fairly easy to fabricate with a MIPS sensor, so I'll mention that today as well. Ferritin sensing. Ferritin is iron. I want to say iron rich. It's not really a protein as such, but it's a. I don't want to say vesicle either, but it's a way of transporting iron around the body. So I'll talk about ferritin sensing today. I'll also talk about creatinine detection. This is a 3-enzyme system. So I'll describe the enzyme kinetics and the screen printed electrodes that you can use. Somebody else is also asking about glucose, lactate, and potassium. They're actually asking where our data sheets are, and for glucose, lactate, and potassium, if you ever Google Zimmer and Peacock glucose data sheet, you'll find it. If you Google Zimmer and Peacock lactate sensor and data sheet, you'll find it. Same for potassium as well. And then lastly, somebody was asking about functionalization of screen printed electrodes. I'll talk about antibodies tonight. Aptamers definitely have done it either in the last couple of weeks, on aptamers. I won't talk about aptamers again, but I will talk about antibodies. And MIPS will actually be mentioned at a few points in this webinar this evening anyway. Like I say, I'm not doing down on MIPS, but it's just with MIPS, I think it's the one that one of the easiest functionalizations to do, but one of the hardest, not one of the hardest, I don't want to be overly too ridiculous with it, but hard to do in a reproducible manner and get specificity out of it would be one of my comments. Just to say, now we've gone through the questions, there's 12 questions, hopefully you could just jump ahead and find a question that's kind of interesting to you. We are doing, if you are a startup or you are interested in the translation of lab work out of the lab and into the real world, come to our webinar on the 25th of November, 1 in the morning, 1 in the afternoon. The 1 in the morning works well for Asia, 1 in the afternoon works for the USA, for example. We're also doing one specifically on wearables, so at ZP. In fact, you will see this evening, or in this live webinar, I'm trying to remember which question it's actually in, but we do have a very exciting new potentiostat that will probably launch in Q1 2025. Tonight is the 23rd of November 2024, so we're in the Q4 of 2024, so this will probably launch in Q1 2025. Anyway, we do webinars on wearable biosensors. I think they're very comprehensive. They're a little long, they're an hour long, but to be fair, somebody told me this week it was an hour long, but it was well worth the watch, so that was nice of them. Academic research, we're also very passionate about the translation of academic research, so we do a webinar every month on the translation of academic research as well. One on the morning, one on the afternoon. Anything I talk about tonight, there'll be links underneath this as well. We are doing an in-person workshop. This will be in Norway. It'll be on wearables and on point of need testing. Point of need testing is this kind of form factor. I do have some wearables in this office with me, but I haven't got them out on the desk this evening. But point of need is this kind of form factor. And this is a very different type of potentiostat. And in fact, if you use that code, that will be underneath this video. You can get 10% off of this for November as well. So let me dive into this a little bit faster. This workshop will be in Norway. It'll be happening on the 22nd and 23rd of Jan, and it will be led by me. So question number 1, somebody's just asked us, can we do electrodes essentially in a circle format? So I've just kind of laid it out, sort of, you don't necessarily have to immediately start with, if you want to make electrodes in a circle, you don't necessarily have to start with bespoke electrodes. I'm using one of our hypervalue carbon electrodes here just to kind of illustrate the kind of format. And this kind of, let's say, idea was actually, like I said, I'm pretty sure it was something like an Abbott or Roche several years ago did this with glucose strips, did the glucose strips in a disc. It wasn't commercially successful, but just FYI. I mean, you can obviously increase the diameter of the disc and you can have, more electrodes around it. I think there's some merit to this idea. I can see applications where that's actually really useful. And the quick answer is, yeah, of course, it's very doable. To make a prototype is quite straightforward. Obviously, to do it at scale and to work out the whole supply chain, that's definitely a different thing. But to knock out a few prototypes is actually quite straightforward to do that. Now, I'm going to answer reproducibility here. So this is really around, when people, we definitely at ZP, when we're making these screen printed electrodes, we're definitely working on ensuring reproducibility. And so when somebody says, oh, I'm not getting reproducibility, of course I'll, definitely take that, and address that. So somebody's trying to do caffeine detection using voltammetry. They're using the hypervalue carbon electrode. They are not using our potentiostat. Now that's probably not the problem, let's say, but just to kind of say that they're not using this. The work that I will present. So if you are interested in this and you are the person who's asking me about the reproducibility and in particular around caffeine, please follow, because I'm going to show you some caffeine data in probably a couple of minutes from now. So they're not using our potentiostat, but they are using our screen printed electrodes. The only one problem with sometimes other people's electronics is ZP is not responsible for the reproducibility of connection, let's say. I mean, I would feel quite responsible for the interaction between a ZP screen printed electrode and a ZP potentiostat. In fact, we put quite a lot of effort into really making sure that we do actually have a good connection. If I could just take this apart, you can see these kind of gold pins that go there. and that's how we make the connection. So it's a really good connection. It's not a slot connection. So many of these handheld potentiostats have this kind of slot, but we have this clicking mechanism. Very good, very reproducible. So I got a suspicion that you might actually have a bit of a problem with connection. But, and it's, as I say, it's very hard to take responsibility for the connection, but I can show you, hang on, for some reproducibility. So as EP, you know, if you come to our academic webinars, etc., I'll talk about how we make these electrodes. I wouldn't even call this at scale. Let me just grab, yeah. The problem is there's lots of people who produce material that looks like this. There's lots of vendors on the market, but the thing that they're really not addressing is reproducibility. And reproducibility in screen-printed electrodes is holding back academic research, and it's certainly holding back translation of academic research actually into products. And so this is something that we do a lot of work on, making sure that our coefficient of variance or our relative standard deviation is, and I think often actually in the range 3 to 6%. So that means that the underlying kind of error that's coming from the screen-printed electrode from ZP will be in the range 3 to 6%. Now this person, I can see the, you know, the, let's say, I'm not going to so much comment on their data, I'll actually comment on our data. So I do show this a lot. For every color, we get a different concentration, and we get, you know, really good calibration and raw data here. And the reason being is because of the underlying reproducibility of the screen-printed electrode. So that's enough on that particular topic. But let me just bring up some new data. So we are using our own electronics. Is really important to say. We are using the same electrode as them. We've been testing with caffeinated and decaffeinated coffee, and it was just by chance that actually we were doing very similar work to them. So what we found out is actually decaffeinated, and then we've actually got coffee with increasing amounts of caffeine in it, and we get really good reproducibility. These are a minimum of these are duplets. We also do triplets, but these are duplets. But you can see that my duplets here at the highest concentration, you can hardly see the separation. At this kind of medium caffeination here, you can hardly see the separation. At this low, you can hardly see the separation. At 0, you can hardly see the separation. That is because the underlying electrodes are so actually reproducible. And so we do actually have, you know, a good linear signal, and with small error bars, and the error bars are due to the sort of 3 to 6% difference between our actual screen-printed electrodes. Now, I will take responsibility if people are using our screen-printed electrodes and our electronics, then I will take, you know, some responsibility on the reproducibility. Of course, once people start functionalizing the surface, you know, start drop casting and doing that kind of stuff, then they're bringing a process into that sensor that is outside of our control, and at which point, you know, you have to take responsibility for reproducibility after that. But ZP, you know, I will, you know, if people sort of say I'm having problems with reproducibility, and then I actually, when I, in this particular instance, realize that we're doing the same work, absolutely show you that these screen-printed electrodes are reproducible. And because they're so reproducible, we were actually able to do this assay so quickly. Why? Because essentially we just had to change the concentration of analyte. Everything else is so controlled, like the screen-printed electrode is so controlled, the electrical connection of the potentiostat so controlled, the potentiostat so reproducible. Everything was controlled, and the only variable was actually the amount of caffeine in the sample. So we were able to develop an assay really quickly, and we've even made a QR code for it. So we do the sensor or potentiostat. This may be a, you know, this is too short a webinar to go directly about that, but I do have 2 webinars coming up. One on the sensor or for commercialization, and one on it on the translation for academic research. And we've actually added caffeine now to the sensor all instrument. So what does that mean? That means that realistically people in industry who want to measure caffeine for some particular reason can actually now use this instrument to measure caffeine. And we did that very quickly. And why is that? Because the sensor all platform, which I really tried to promote to people, and you can get 10% off this month for it as well, is a very powerful platform for translation of lab-based experiments into point-of-need testing that can benefit, most importantly, benefit society. So yeah, actually I've just said it, but there's the QR code. We just added it now. Now, if you're not sure about these QR codes, come to one of our other webinars, one on academic research or one on for startups on the translation of academic research into products. Just a bit of fun this one is. So I quite like this because I get a nice email now and then from some guys in Hungary, and they basically develop their own electronics, and at ZP we develop our own electronics as well. They're in an academic setting, but they're kind of sweet and not sweet. They're nice people, and they asked me to comment because somebody had sent them, I think, this data, and actually they had quite a nice Nyquist plot, which was sort of showing that something was being oxidized, and then it had this kind of tail, which has probably an approximate. I say probably because I'm just looking. Their units are. The scales are slightly different here, but this looks like a sort of diffusional process. And they said, well, what's going on here? And just FYI, we also do really nice electronics as well. In fact, this is a new wearable potentiostat that we'll probably end up delivering in Q1 2025. Definitely watch the channel. Definitely watch the channel for discounts, etc. And I told them it's probably a sorbic acid that they're oxidizing. Now, I don't have a lot of details from them, because you can have non-Faradaic impedance spectroscopy and Faradaic impedance spectroscopy. Faradaic is easy to define. You kind of do Faradaic impedance spectroscopy at a potential of where something is being oxidized or reduced. In this particular case, I kind of just took a guess at it and said, well, they're possibly looking at a sorbic acid. I don't know, because I literally have only got the picture. But I made a comment. I didn't hear back from them. I don't often hear back from them on these things. I think they just... they were just kind of asking a chemist, what's your best guess at what's going on here? And I said, well, it's an apple. Maybe it's a sorbic acid. I'd love to hear other people's thoughts on that actually as well. Question number 4, we are getting inquiries now about this new lead system. So it's a little bit crazy, this Sensi-All platform, that it's a very, very powerful... It is actually a potentiostat. And with the QR codes, you can do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep, cyclic voltammetry, square wave voltammetry, but also it can actually then be used to do industrially relevant assays like chili, ginger, lead, which is just coming out, caffeine, which I just mentioned. We just put that on the platform as well. So a very powerful platform, and we are starting to now get lots of inquiries about the lead. And just to kind of, people want to see it in action, which is, somebody said, can I see this thing in action? And have said to them, in fact, we do now have a live video, and I realize I haven't put a link in this, but I do want to say there is a live video online where we run the Sensi-All, we do the detection of lead, and in fact, I think I'm actually going to do a similar video on the detection of caffeine pretty soon as well. What I really like about what we're trying to do at ZP is, I do see, so this is a sort of screen printed electrode. It's in a nice sort of cartridge, but it's just the way I can just place it into the instrument. Just click this button up like this, and it just clicks into place. See, it gives a really good user experience. And I have seen, some things online where people have kind of making their own screw-printed electrodes. They're very flexible, and they're trying to shove them in this slot. And the whole thing is just buckling, because you're trying to, shove quite a thin piece into quite a tight slot, and it buckles. And so you've got to put yourself in the position of, a normal, let's say, user. They don't want to be, they need things to be quite quick and easy, So there's a lot of... great ergonomic design in that, the way you can hold it, you can hold it without actually touching the electrode itself, and the way we can just actually click these then actually into the instrument. So I think they make for quite a elegant device. But we do have a nice video online where now actually we do a live streaming let's say demo of actually testing the lead, and we talk through the science of what we're actually up to, and we actually talk about that the Sensi-All platform as well. So I will put a link to this video underneath this one as well. And the great thing about the Sensi-All platform is you actually can get to see the raw data. You get the result on the phone, and you also get to see the result up in our cloud system called Julie. Julie is truly a unique, very powerful technology for, I think it's the only technology really around for receiving electrochemical, let's say, data. So it's very, something we've been developing for at least 6 years. Somebody's interested in measuring pH. They were also interested in measuring glucose and lactate, but I'll just address pH first of all. There's plenty of material online when we talk about our pH sensors, but really the technique is open circuit potentiometry. Now, I am more reluctant to support people's use of our pH sensors using their own electronics. Now, in this particular case, these people have been successful because I think potentiometric measurements and potentiometric circuits are probably one of the easier things to do. But I can't overly support people using our biosensors on their electronics. The problem is, if your electronics are not functioning correctly, then you're sort of asking us to support you whilst you on something that you really should be the masters of, let's say. But because at ZP we do have electronics, you can either be using the Sense It All point of care device, which I'm moving around in that little mini screen, or you can be using our single purpose biosensor circuit, which I will also try to remember to link to as well. So at ZP we do have electronics, and so I know that they will work and it's easy for me to support. But when people are having problems with saying, I made my own circuit and the glucose sensor is not responding. Glucose sensors respond. It's robust technology. It's the electronics that's up, but it's just the way it is. And the nice thing as well is that ZP we don't just ship the sensors. We have actually tested part of the batch before we ship it. So we got glucose and lactate, and those are actually run on amperometry. So as ZP does sell its biosensors on the website, those biosensors that we sell on the website are designed to get you to some sort of proof of principle. I can define that a bit more. It's technology readiness level number 3, TRL3. TRL3 is not TRL9. TRL9 means boom, you're on the market, you're good to go. What we put on the web store is not intended for that. It's intended only for people's R&D purposes. And actually, that's not a terrible claim. Just out of interest, a lot of people buy materials from Sigma Aldrich. Actually, these days known as Merck, or Merck bought them rather. But if you read their terms and conditions, you actually find out that they're only intended for research purposes. And if you want to use them in a medical product, you actually have to get their permission. So at ZP, I went very clear that what we sell on the web store, you do not have our permission to use it in medical products. Why? Because I can't guarantee every scenario that you're actually going to use them in. You really need to be properly engaged with a company if you're going to use its products in a medical device, especially ZP. We're ISO 13485, so we'd have to have a quality agreement between us, and those quality agreements only can really come about if people are well funded and have a proper business plan and the funding in place to do it. Anyway, that said, if you're using pH sensors from ZP, then you're probably going to be doing open circuit potentiometry, and if you're using glucose and lactate, it's going to be amperometry. We have plenty of electronics to drive these sensors. You can get them from ZP. If you're using your own sensors, you are, let's say, more on your own, and the support we can give is a little bit minimal because we can't fix the electronic problems that you might otherwise have. Laser-induced graphene, this is kind of interesting. Graphene's an interesting material. I mean, I generally think that it does, help with a little bit with sensitivity, etc. I think the most valuable asset of graphene is that if you do something on graphene, then you could sometimes get it, more easily published. So there's a benefit to academia to work with graphene. Sometimes, in my own time, there's been single wall carbon nanotubes, there's been multi-wall carbon nanotubes. Before that, there was sort of, Buckminster fullerene. So these allotropes of carbon do come through, and now we've got graphene at the moment. But this paper is kind of interesting because they made a graphene sensor using laser-induced, they call it LIG, laser-induced graphene, which I thought was actually quite neat. We do make a graphene sensor ourselves at ZP. I must admit, we don't use LIG. But reading that paper, actually you could use that technique. And I was a bit curious, really, and I was wondering about what the authors thought, that they were using the laser-induced, or they were generating the laser-induced graphene by shining a laser onto polyimide. And I can understand, their argument, which is there's lots of aromatic rings in there, and therefore they can produce this graphene. I was wondering what's wrong with shining the laser actually onto the graphite. So for example, at ZP, we make a very nice reproducible carbon 501 graphite electrode. What would happen if you fire the laser onto that? I can understand, that if you put a lot of energy onto carbon, it becomes carbon dioxide, and, is that the issue? Or is there another reason? So I was just wondering why the graphite couldn't be the source of aromatic rings. Maybe because they're not aromatic. Well, I'm not sure. Graphite is an interesting material. It's very amorphous. So actually, that's not fair. It's crystalline. But anyway, I'd like to talk to the authors about why we couldn't just do a laser-induced graphene by using the graphite electrode on a 501. So I might actually reach out to them about that. This molecular imprinted polymers. As I say, I like MIPs because they're fairly easy to fabricate. I do worry about the specificity, but there's always a balance in life, about ease to make, easy to use, but does it give the specificity? But that said, I wanted to sort of follow this. Somebody was asking me how we would translate this paper into a product, and I thought well, it was quite straightforward because they're doing sort of an electropolymerization of pyrrole into polypyrrole, probably in the presence of graphene oxide and iron oxide, and I suspect that the polypyrrole is kind of polymerizing and maybe entrapping or encapsulating these graphene oxide composite as well, and they're doing it on top of a gold electrode. So I do understand the paper. So with the gold electrode, ZP does have a good gold electrode, a very reproducible gold electrode. So that would be, one place to do it. Easy enough to do the electropolymerization on top of that gold electrode. And then you can just follow the rest of their process. I was just showing here that, in fact, this very new type of potentiostat, the Sensi-All potentiostat, does have cyclovoltammetry in its arsenal as well. So we can quite easily scan, whoops a daisy, we can quite easily, that's square wave as well, because I scanned that QR code, linear sweep there, I want to get that one there, square wave. I've got them all too close to one another. I'm just doing this for a bit of fun now. There we are, cyclovoltammetry. What I was going to say, sorry. Yeah, so we can do that functionalization step where they do electropolymerization probably by cyclovoltammetry also on the Sensi-All as well. And that is a powerful instrument because later on they do EIS, and we can do it all on something that's much more, let's say, elegant and much more translatable. This is something that even ZP uses in some of its product offering. So it's a very unique type of potentiostat, and this potentiostat is not some sort of third-party potentiostat dressed up in a pretty box with their own graphic on it. No, this is a super new type of potentiostat, only runs off a smartphone and is connected to the cloud, and we use it in already now for doing lead and chili sensing. I suspect that caffeine sensing will come to it soon as well. So we use it as a product and as a potentiostat in our own labs, and we sell it as a potentiostat to our colleagues. And actually, I'll put a discount code underneath this video. You can get it for discount, and it works really nicely with these very handleable, easy to use, sensors. If you're going to make a product that actually people can use, and none of this none of this kind of trying to put an electrode in an awkward slot on the front of the potentiostat. It just goes in there, clicks in, and it is beautifully done. Right, so the process in the paper is quite easy to translate onto one of our gold electrodes. I've read this, and this is all fairly straightforward. And at the end of it, actually, they use EIS, impedance spectroscopy, so we can also both functionalize the electrodes on the Sensi-All potentiostat, but also do analysis on the Sensi-All potentiostat as well. And most importantly, the instrument will analyze the curves, the EIS curves, and actually turn it into Lysozyme, I should say, concentration. So you're not left there hanging with EIS. It will actually turn the EIS into an actual concentration, so it will be much more useful for, like, say, end users. So if you are interested in commercializing that assay, do let us know about it. Yeah, so I mean, to describe the workflow, we've got these electrodes. You would have functionalized them to make them specific to Lysozyme. The electrodes will click into the instrument. You'll put a sample on there. Only takes 50 microliters. We'll have set up a QR code accordingly, which will then tell the app what to do. The app will tell the meter what to do. The meter will send the data back to the app. The data will get sent into the cloud system called Julie, where we'll process it, turn it into a concentration, and send it back to the phone. It's a very elegant way of going from technology readiness level number 3. So most scientific papers actually finish with technology readiness level number 3, but actually it will process the data through this cloud system called Julie and actually turn it into a genuine concentration, which is much more useful for, you know, people in the food industry, for example. Next question was about ferritin. So ferritin is a way, I think, the body uses to transport iron, and somebody was asking whether we could. Now this diagram does not belong to this paper, so my apologies for that. But the reason I bring this up is, you know, this is an easy to follow paper, easy enough to follow paper, but it didn't have the process in a diagram form. And I just want to say to authors in general that when you put these kind of illustrations in, where you kind of say this is step 1, this is step 2, this is step 3, this is step 4, you can see how easy that is to actually follow. So, you know, in this busy age where we want people to engage with our work, you know, quite readily, it is actually quite a good idea to put a graphic like that in. This graphic does not belong to that paper, but I'm just using it to illustrate how actually when you do put a graphic in like that, it is, let's say, easier to follow what's in the paper. Now, this paper didn't have that kind of graphic. I wish actually I'd put the graphic together. But I did actually read the paper. They were using a kind of ferrocyanide marker. They were using a 2D material, this kind of tungsten sulfide. They were using the antibody to ferritin, so anti-ferritin. And they were able to get a assay out of it. And this is a kind of blocking assay. And I'm pretty sure that I have actually put a, I've got some, hopefully I've put some, yeah, I do have a mechanism for this. So at ZP, we also do these kind of assays. They're quite straightforward to do. In fact, I was having a conversation with somebody the other day and I said, you know, in fact, I think everyone's doing these kind of assays these days. I've got a suspicion that these assays were done before ZP did them, but we heavily started promoting these about 10 years ago, and now I do see quite a few people doing these kind of assays. So you take a gold electrode, you put your aptamer or your antibody on there. In this case, they had an anti-ferritin, they had ferritin, so it blocks the sensor. And then they have a ferrocyanide, which wants to access the electrode in their particular case, but because of the blocking by the ferritin, it slightly blocks the surface, and then they get a signal, and you can read that signal. They were probably reading it by differential pulse voltammetry, though just a plug, and also they say, don't forget there's a 10% discount code off this. Where are we going? Yeah. You could, I think it's a personal preference for me, but I also quite like square wave voltammetry. But in fact, they could have also used EIS as well. That's linear sweep. Yeah, impedance spectroscopy as well. The reason I bring those up is just because differential pulse voltammetry, my personal preference is square wave voltammetry. They're pretty similar. And then sometimes if you want an extra bit of sensitivity, EIS. But EIS can be a little bit too sensitive. But all that said, so their mechanism is basically a blocking assay. So when they have binding, the signal slightly goes down, and that's what's happening in that particular paper. Whoops-a-daisy, I realize that I'm not sharing the right screen. So let me just I'll just run through that really quickly again. So they take a gold electrode, they functionalize it accordingly. They get to having anti-ferritin on the surface. The ferritin binds to the surface. The ferrocyanide reporting molecule wants to get to the surface, and when there's not much binding, they will get a peak, which they determine by DPV, differential pulse voltammetry. We would have used square wave voltammetry. It's just a personal preference, but this instrument is very powerful for it and does a nice job, because actually it would have turned the decrease in signal that they're getting actually into a concentration of that ferritin. So they were actually not finished at TRL3. A TRL3, by my definition, is you've got raw signal and you've got calibration. It would have actually taken the raw signal, put it through that calibration, and returned them a concentration of the protein. And then they could have gone and started giving it to clinicians, because now the clinician is able to get a concentration on their phone as opposed to just raw signal. But that's how I would go about commercializing it. But of course, well, that's how I go about commercializing. Anyway, with that blocking, the signal essentially goes down. So, without blocking, you may have that kind of signal, and then with blocking, the signal does that. So that's the kind of mechanism behind that particular paper. Question number 10. Somebody wants to, not a group wants to make a sense of a creatinine rather. This is a 3-enzyme system. Not straightforward. Well, there's plenty of papers out there. You wouldn't be the first ones to be trying this. But you've got this creatinine amido hydrolase. So what's happening there is it's turning creatinine into creatine. Sorry about this. I always get creatinine and creatine. It just mixes them up a bit. I don't know what it is. It's some sort of, I don't want to say mouthful, but I don't want to say dyslexia, because people generally do have dyslexia. Maybe it's just bad reading. But we've got this creatinine trying to get to creatine, and it's through the enzyme. So you do need this CNH, this creatinine amido hydrolase. And what that's doing is it's just hydrolyzing a bond here and basically doing a ring open. So this creatine is in its sort of ring form, and in the presence of the enzyme, the ring form essentially just opens up. So that's the opened up kind of molecule. So that's the first, let's say, stage. The next stage is a further hydrolysis of the creatine into sarcosine. Sarcosine. So it gets essentially splitting here, and we get the sarcosine, and at that point then there's an oxidase for this. Call it SOD, sarcosine oxidase. Oxidases are well liked by ZP and are well liked in the the bioelectrochemistry community, because they often produce hydrogen peroxide. Now this group wants to build everything itself, completely fine. All I can say is keep it simple. In fact, now I remember what I wanted to say. It sounds really strange, right? If you've got limited funds and limited time, you have to be realistic in what you can actually achieve. So I have a super strong suspicion that creatinine is actually electrochemically active in its own right. So that means you can probably do voltammetry on it and actually find out that you get a peak for creatinine. Now, the reason that doesn't then become a biosensor is because the electrode will detect it, but it won't be specific. But if you're doing a student project and you have very limited resources and very limited time, it may be just enough just to do voltammetry on the creatinine. Right, so just know you can actually detect creatinine without going through any of these enzymes. Now, if you're making a product, let's say, and you're really making it for detecting creatinine in blood or urine or somewhere else, then you will need that enzyme reaction because you want to get the specificity out of it. So there, now I'm just showing you the next level of complexity. It's harder for a student group with limited resources to do this, but it is possible. So I give you super simple. Actually, creatinine itself is probably electrochemically active. You could do voltammetry on your buffer. You add in some creatinine, let's say 5 millimolar, and you'll probably see quite a nice peak develop. In fact, take a look at my caffeine work earlier on as an example of kind of, we showed decaf, we showed caffeinated coffee, and you'll see that there. So you may have to take super simple because you're not super well funded and you need to achieve a tick box. And the tick box is we made a sensor for it. But you could then be criticized for it being non-specific. But are you really trying to make a medical product at this stage, or actually you just trying to learn your trade? And if you're learning your trade, what I'm suggesting is fine. Just do super simple. The next level of complexity is this enzyme, but it's quite a step up, as you can see, because you've got to source these 3 enzymes. They're probably not super super cheap either, I got a suspicion. But these kind of papers, there's there's lots of these. There's lots of sort of this type of paper, and it finishes with hydrogen peroxide. Now, when it finishes with hydrogen peroxide, you can detect hydrogen peroxide on a platinum electrode, and I've essentially got a link to a platinum electrode here. Now, if you're a commercial company, you're really trying to kind of get cost out of this product, you might want to go for a carbon electrode, at which point you have to add a mediator, and possibly adding something like a ferricyanide mediator will then allow you to use a carbon electrode and a lower poise potential. So there's another complexity again. And I'll put a link to a kind of carbon electrode there as well, and a link to our potentiostat. Don't forget we're doing a 10% discount, but this particular group is not super well funded. So let me stop for a second and just do sort of some thoughts. So I think sometimes with projects, with student projects, you've got to think, how much time have they given us? How much money have they given us? What's our level of skill? And that's okay. It's no criticism of anyone. You can detect creatinine. Just look at our caffeine work in a few slides above, where you can actually see that we essentially had a sample without any caffeine in it, then we added caffeine and you saw the signal go up. You can do that kind of experiment with creatinine as well, and you will probably detect it. And you can probably do that on a carbon electrode without much modification, or any modification, actually. And that's super simple. But sometimes you'll be judged that, oh, you made it too simple. And that's the problem, but okay. So then you may want to, you may want to think, okay, it's too simple. I'm worried about it's not going to be specific enough, but it'll be specific enough in the context of buffer solutions. Okay, so you can then build this up with this complexity. The next level of complexity is to put those three enzymes in place on the electrode and to turn the creatinine effectively into hydrogen peroxide. But you've got to source those enzymes, you've got to get them down, you've got to get the whole thing working. Quite an effort, okay? And you can detect hydrogen peroxide on a platinum electrode, so that's the next level of complexity. And then there's a little bit of complexity just beyond that, where actually, like if I was commercially doing this and somebody said I want a low-cost carbon electrode, low cost and carbon go together, low cost and platinum do not go together. They said I want a low-cost electrode. Then I would actually put a mediator in there to help get that hydrogen peroxide essentially oxidized on a carbon electrode. So there's never a short answer, and it's not a short answer, but I have given you essentially three ideas. Creatinine, just do it on a carbon electrode without any enzymes. The enzyme system, at which point you detect it on platinum, or the kind of most commercially, I say viable, but commercially, useful way is adding the mediator at the end and doing it on a carbon electrode. So I hope that is useful. Now, at ZP, obviously, we're a commercial organization, but I do want to sort of just put a shout out there that we're, there's probably there's no chance of ZP getting any kind of essentially any orders from that, but you can see that we will try and support people if they ask. Now, somebody's asking about our data sheet, so I just want to be very clear that our data sheets actually are available on the website. So every sensor this person is asking for, glucose, lactate, the data sheets are definitely on the website. So I've taken screenshots and I'm using the arrow to point and just say, honestly, I've got a link for each one of these. I've got a screenshot. I'm showing you where the data sheets are. So if you are interested in ZP sensors, what we have in the public domain is in these data sheets and on these websites. And if you have any questions, well, hopefully that is the questions answered in this particular case. Now I'm going to do a quick, so can you put electrodes in a wheel type configuration? Absolutely you can. I think it's actually been done commercially with glucose sensors. Product wasn't, I don't think, that commercially successful. So I'm not sure it's a great idea. Measuring caffeine, our ZP screen printed electrodes are very reproducible. Just by coincidence, the person who was having some problems with reproducibility, in parallel with them, ZP was doing it. And in fact, we've even gone on to make a QR code and put it on the Sensi-All platform. EIS impedance of fruit, I've got a suspicion that a molecule that's fairly in abundance in fruit is ascorbic acid. It's intrinsically electrochemically active. That would be one of the suspects for why you're getting such nice impedance spectroscopy in that fruit. The analysis of lead is definitely something that now can be done on the Sensi-All platform. pH glucose and lactate. pH is potentiometric. Glucose and lactate is amperometric. But if you're struggling, especially on the glucose sensor, which is a really robust guy, then I have a super strong suspicion your electronics are slightly up. Super interested in hearing from the authors of that laser-induced graphene. Why can we not shine a light on the graphite electrodes and actually turn those into graphene electrodes? Super interested to hear. I mean, I'm sure they've tried it, but I'd love to hear why. Maybe it just ablates all the graphite off, and you just essentially just turn it into carbon dioxide. Lysozyme, like I say, I do sometimes worry about MIPs and their specificity, but it is an easy assay. It's an easy sensor to make on those gold electrodes. Actually, no, they were doing, I can't remember what electrodes they were using, but it's an easy one to do. The ferritin is also easy to do. The creatinine is a hard one because, like, if I was a undergraduate or graduate student at the moment, I would do it just creatinine straight on a carbon electrode. Look at that caffeine work that we did earlier on for inspiration. I just don't like it because I know what will happen. The judges will judge you. So you have to figure out what the judges are going to judge you on effectively. And if they then try to argue that you didn't build specificity, then you have to put those 3 enzymes in. I think you can do that, and then you can detect the hydroperoxide on the platinum. Commercially, then we would probably actually do it on a carbon, because you should never try to make a low-cost sensor on a platinum electrode. You can't. Platinum is made when stars go supernova. I think just that statement alone tells you how valuable platinum is. Platinum is made when stars go supernova. It's stardust. Most of the heavy elements heavier elements are actually stardust. But so I shouldn't overplay that statement. But that's where platinum comes from. It's a carbon is a much more abundant material. So we would actually try to build on a carbon electrode, but then we have to put a mediator into the system as well. If you are looking for data sheets from ZP, you will definitely find them on our website. I thought I'd missed a question. So question number 12 is going to come last, and I apologize for that. Question number 12, functionalizing screen printed electrodes. Now, they did say antibodies, aptamers, and MIPs. In fact, we do actually have quite a nice paper on this. I think I've slightly changed my mind these days that if you're going to follow this paper, use our carbon 501 electrodes. I'm sorry that I put this one slightly out of order, but with that said, let me dive into it a little bit. So we do have a carbon 501 screen printed electrode. Carbon is super cheap, not super cheap, I should be careful with that statement. Carbon is much lower cost than gold. So people would often do an antibody on a gold electrode, but I would actually suggest you try the graphite electrode. Use a molecule called pyrene NHS. Ironically, I've mentioned Sigma Aldrich earlier on, which got bought by Merck, so you can get this from Merck. You can couple the antibody to the NHS group, and you can block with something like chitosan. I have mentioned our electronics quite a bit. This electronics will allow you to do the kind of characterization during the development of that sensor, and it would also allow you to do the detection at the end of it. And don't forget, we've got a 10% discount on this month. I'll put that code underneath the video as well. So this is a paper that you can follow, and it's essentially working like a blocking assay. Rather ironically, I showed blocking assays earlier on, where when you blocked, the signal decreased. I oversimplified it because sometimes you can have blocking assays where the signal increases. When I say it increases as well, it's the magnitude that's increasing. You could ask me, why is that happening? Well, this was an unusual piece of work where actually we had an electrostatic repulsion, which got slightly neutralized in the binding. So even though we were increasing the steric hindrance, we were decreasing the electrostatic repulsion. In fact, we ended up getting more signal. Unusual. Earlier on in one of those MIPS papers, they would definitely do a blocking assay, and their signal decreased with binding, whereas actually it was a Ferritin paper. But in this one, actually the signal went up. So I apologize for getting that slightly out of order, but that was question number 12. And obviously, I would ask you to use our Sensi or Potentiostat and use our screen printed electrodes. I think the carbon 501 would be a good platform for you to build upon. Why is that? Because of the reproducibility. Have I proven reproducibility in this particular webinar? Yeah, go back and look at question number 2, because there I was defending in a good way our electrode because somebody was having problems, and I genuinely said, no, honestly, our screen-printed electrodes are really good. They are using a different potentiostat with different connectors. They are using our screen-printed electrodes. So I do ask people that use our instruments because then it's easy for me to support the instruments. I just want to say thank you. If you have any questions, don't hesitate to reach out to us. I'm not even sure how long this has been going on for, but I've got a suspicion 51 minutes. Okay, so any questions, reach out to ZP. You can see we do put a lot of effort into answering questions, and if you've got any questions and you get them in the next week, you'll probably have them answered next weekend. Okay, thanks very much.